Okay, let's look at the section 10.5. Right, this section talks about the restriction of a function to a certain set, and also a lemma. Right, let's first look at the restriction of a function. Right, so let's say you have a function f from a to b, and C is a subset of the domain A. Right, then we can restrict the function f to a set C. Right, so you're just taking all the elements in the function such that x is in C. Right, so if you look at a picture, say you have a set A like that, say 1, 2, 3, and a set B, so that's going to be a codomain, say A, B, C, and let's say 1 goes to B, and 2 goes to C, and 3 goes to A, or something like that. Let's say this is the function f. Right? So restriction of f to a set, let's say set C is a set with 1 and 2. So let's say this is a set C. Right? So that would be, so you're restricting the function, so you're only looking at these guys. All right? So restriction of this function to a set C would be a function that maps 1 to B and 2 to C, and that's it, right? So this is the f restricted to C, all right? So that's just a restriction, all right? Then let's look at this lemma, all right? So you have two functions. F goes from a function from A to B, and G is a function from C to D. Right? A and C are disjoint, and B and D are disjoint. Right? So we're looking at this situation. So you have set A like that, and here's set B. Right? There's a function from here to there, so that's function f. And you have another function g from C to D, totally separate, right? And what we do is we're going to put them together by defining a function h. So h is a function from A union C. So we put these guys together. So here, these guys together, and as a domain, and put B and D together as a codomain, right? Then we define a function from A union C to B union D, right? That's h, right? So we define a function h by, right? H of x is the same thing, same as f of x if x is in A, and h of x is the same thing as g of x if x is in C, right? Then the statement is, first one, if f and g are 1 to 1, then so is h. So h is also 1 to 1, right? And second statement is if f and g are onto, then h is also onto, right? So let's prove the first statement, right? So we assume one, let's say, we assume that the f is 1 to 1, right? So this is given, all right, and 2. G is also 1 to 1, right? This is another given, right? So let's move up so that we have more room, right? So let's try to prove that, right? So let's try to see if h is 1 to 1. So we're going to have to start with 3, right? So let's start with h of x1 is equal to h of x2. Right? So we're going to start with that. So this is also given. Right? And the fourth. Right? So we have to look at the cases. So this is this could be in either in B or D. Right? So let's look at the cases. So say this is case one. Right? H1, h of x1 and h of x2 happens to be in B. Right? So this is case one. Case number one. If it's in B, then that means that the only function that hits is f. Hits B is f. So we know that the 5. So h of x1 is the same as f of x1. And h of x2 is actually f of x2. Right? So that comes from line number 4. All right. But we know that the f is 1 to 1, so from line number 1, and we have 6, we have x1 is equal to x2, right? This is exactly what we wanted to show. All right, how about case 2? So 7, all right, if h of x1 and h of x2 turns out to be in D, right? So this would be case 2. Right, then 8. Right, only function that hits D is G. So it's going to be G of x1 and G of x2. Right, so this comes from 7. All right, but the G is 1 to 1, so which comes from line 2. So we know that x1 has to be equal to x2. Right? So therefore, either case, we could get x1 equals x2. We know that h is 1, 2, 1. Right? So that comes from, let's see, so we have a 3 implies, actually, maybe, yes, 3 implies that x1 equals x2, so 6, and also 9. Right? Right, so that's that. So let's prove second statement. Proof of number 2. All right, let's move it up so that we have more room. All right, so the hypothesis is 1. All right, f is onto. All right, so this is given. All right, number 2. G is also onto. All right, so this is given. All right, so we have to show that h is also onto. So start with 3. All right, let's choose any element, say y, in B union D. Right? So this is also given. Right? So there are a couple cases, 4. So let's assume that, let's look at the case that the y is in B. Right? Right? If y is in B, we know that 5, right, there exists, right, some x in A such that, right, h of x is same thing as f of x if x is in x is in A. So, but the f of x is onto, so we know that there's some element x which is equal to, exactly equal to y, right? So since this is f is onto, right? So we got that. And case 2, we have to look out. Sorry, I should have said this is. Let's call this guy instead of giving case 1, right? Then 6. What happens if y happens to be in D? So this is in case 2, all right? But if y is in D, then there exists an element in B. So it's a 7, right? Maybe I should say there exists an element X in C, sorry, such that, right, h of x and g of x are the same thing, and is equal to this y, right? So that comes from the fact that g is onto, right? But either way, we know that h is onto, so therefore h is onto, right? Which comes from, let's see, 3, and then we know that they exist, so line 5 and also line 7, right? All right, so if you know that the F and G are both onto, then H is going to be onto, right? So we could prove these two statements right here. All right, that's it. I hope that this was clear.